Welcome to this fourth lecture in this series of videos on textile printing.
In this lecture, we are going to discuss about the specific requirements that need to be fulfilled when we are preparing a fabric for printing. These requirements include the fabric surface should be free from any impurities, whether these impurities are sitting on the surface like dust or lint, for example, or any loose threads or fibers, those are called surface impurities, or any subsurface impurities, those are the impurities that are embedded within the structure of the fabric. The layout of the weft threads should be correct. The fabric shrinkage should be controlled as much as possible before printing, and the dimensional stability of the fabric should be improved. The fabric should be free of any creases during printing, and there can be some special requirements as in inkjet printing, which we will see in detail in the topic of inkjet printing. Now let's have a look at these requirements one by one. So as we have discussed, the first requirement is to ensure that the fabric is free from any surface or subsurface impurities. This point generally refers to the pre-treatment of a fabric. And that's why I've mentioned here that you can review some of the key concepts in your course of TS245, which we have already studied. However, I'm going to discuss this point briefly. We know that desizing and scouring operations remove hydrophobic materials from the surface of a fiber or a yarn. If these hydrophobic materials, such as waxes or sizing chemicals, are left on the surface, then they will interfere with the printing ink, and the absorption and penetration of ink will be affected. So as shown in the image here, before desizing and scouring, the added impurities sit on the surface of the yarns or fibers. And after singeing and desizing, the yarn surface is completely clean. So now the ink, the printing ink, can directly interact with the substrate, which is important for proper printing. You are well aware of a pre-treatment operation known as bleaching. Generally, it is considered that the primary objective of a bleaching operation is to improve the whiteness of the fabric and to improve its absorption as well. Optionally, we carry out mercerization process as part of the pre-treatment operations. Mercerization is known to improve the whiteness of the fabric. It is known to improve the dimensional stability, and it is argued that mercerization reduces hairiness on the surface of the fabric. So in a way, if we carry out mercerization, we can expect that the fabric surface will become smoother. The second requirement that needs to be fulfilled when we are preparing a fabric for printing is to ensure that the layout of the weft threads is correct. Let's have a look at this. When a fabric is woven, for example, the weft yarns are inserted exactly perpendicular to the warp yarns as shown in the image here. However, right after weaving, the fabric is subjected to several different processes, and in these processes, a lot of pulling forces or stresses are applied on the fabric. Most of these stresses are applied, of course, during the wet processing of a fabric, and more specifically during pre-treatment operations such as bleaching. You have studied in your previous courses that continuous open bit continuous bleaching machines can contain well over 100 meters of fabric at a time. So the fabric is pulled through several dozen rollers, and of course, in this process, while the fabric is being pulled, a lot of force is exerted on the weft yarns. As a result of this, the layout of the weft threads can be disturbed. So ideally, as we have just discussed, that weft yarns are exactly perpendicular to the warp yarns. Such a fabric is called a defect-free fabric, or you can say a distortion-free fabric. But the stresses which we have just discussed, such as those that are exerted during bleaching, can result in the wefts acquiring a curved profile. This particular type of distortion of wefts is known as a bow distortion. There is another possibility. The stresses or the forces, the pulling forces that are applied on the fabric can result in a distortion known as the skew distortion. In this case, as you can see in the image here, this one over here, the weft yarns are a straight line, but that straight line is no longer perpendicular to the warps. So in this image here, you can expect that of course the warp yarns will be like this. So we are talking about this angle here. The angle between the warp yarns and the weft yarns is no longer 90 degrees, despite the fact that the weft yarns are a straight line. This distortion is called a skew distortion. There are other types of distortions as well that can occur in a fabric during processing, but the bow and skew distortions that we have just discussed are the more common ones. This image here is showing different possibilities of the distortions that can occur in a weft thread. Now, the simple bow and skew and their simple combinations can be removed from the weft threads. But a particular type of distortions, known as compound distortions, cannot be removed if they are once produced in the weft yarns. Let's have a look at this image here, which is showing different distortions. Notice this arrow here. This is representing the direction in which, let's say, the fabric is moving. So if this is the direction of movement of fabric, then this particular distortion here, the first one, is called a reversed bow because the curvature is in the reverse direction, if you like. The next one, as you can perhaps expect, is a forward bow because the curvature of the weft threads is in the forward direction relative to the direction of movement of the fabric. The next one over here is a skew, and because this is on the right hand side of the fabric from the angle from which we are viewing it, this can be regarded as a right hand skew. The next one becomes obvious. It's known as a left hand skew. Now let's look at the next one. This is a skewed bow or a bowed skew. So if you look closely at this distortion, you will realize that it's a combination of a bow and a skew. More specifically, it's a combination of a forward bow and a left-hand skew. So all these distortions, the five that I've discussed, are either simple bow or skew or a combination of simple bow and skew, and these can be removed. The next one that you see in the diagram is called a double bow. As the name implies, you can see that this distortion is in such a way that the weft has two smaller bows in it along the width of the fabric. The next one over here is called S bow. As we have discussed, these are the ones that can be removed on certain machines that we use in textile processing. And these two are generally considered to be permanent or they cannot be removed. However, I've put an asterisk over this point because these days there are certain devices available which claim to actually which are claimed to be able to remove these distortions from weft threads. We are going to look at this in greater detail in the next lecture when we discuss about removal of weft distortions from the fabric. Now, what is the problem if weft distortions are not removed from the fabric prior to printing? So if this is not done prior to printing, then it can result in deviation of printed designs later on. Let's try to understand this point with the help of some images. So this is the fabric. The width and length wise directions are marked here. And you can see that the wefts are shown in the form of a reverse bow in this particular fabric. Now let's say if we print widthwise stripe design on this fabric, it will look something like this. And if at a later stage The wefts are straightened out due to any reason. The printed design, which were widthwise straight lines, will be distorted like this. So this image, this set of images show us that why it is important to remove weft distortions and how they can potentially result in printed design deviation if they are not corrected prior to printing. Another case that is related to correct layout of weft threads is this one. It is possible that printing was done on a fabric in which the weft threads were in their ideal layout, that is straight and perpendicular to the warp yarns. But if any distortions in the wefts occur after printing, then still the design will be distorted. This is the scan of an actual printed fabric. So you can see that the fabric is straight and the design, of course, is printed accordingly. If this fabric is skewed after printing for any reason, then the design is also distorted. So if you look closely, you will realize that there is a difference in the shape of this motif here on the undistorted fabric and on the distorted fabric. So this is not what we want. So let me summarize this. It is important in the context of printing to ensure that there are no weft distortions in the fabric. Our main aim is to ensure that weft distortions are removed prior to printing in order to avoid any design deviations later on. The other case that is possible is that printing is done on a fabric in which the weft layout is correct, but after printing, the wefts are distorted. So we have to understand that even in this case, the design will still be distorted and it is not acceptable in terms of printing quality. The third important requirement to be fulfilled in fabric preparation for printing is to control the shrinkage of the fabric and to improve its dimensional stability. This is because excessive shrinkage of the fabric during printing can result in printing faults. Now let's again try to understand this point with the help of some images. Let's say this is an unprinted fabric and you want to print this design on this fabric. So you want to print a red colored letter A on the fabric and a light blue background on the fabric. Let's say you first print the background color. So of course, in the image here, you can see that the letter A, the area where letter A is to be printed is still white, while the background is printed blue. Now, normally we don't do this. We print the smaller designs first and the background at the end. But just for the explanation of this point related to fabric shrinkage, I'm giving this example. So in this case, we have printed the background first, and we are now going to print the letter A on this. Now, because we have applied a lot of printing ink on the fabric, if the shrinkage of the fabric is not controlled prior to printing, the fabric will shrink because the printing inks contain a lot of water in them. So this will be the position of the fabric after the background, the light blue background is printed on it. And now when we want to print letter A in a particular size, it won't fit in the wide areas. This problem has occurred because the fabric shrinkage was too much after printing of a certain color, and therefore the positioning or the placement of the subsequent colors on the fabric is affected. Now let's have a look at how fabric shrinkage and dimensional stability are improved. This is done using by a process known as heat setting. The term heat setting is applicable for thermoplastic polymers only. In the case of textiles, one very good example of such polymers is polyester. So normally we do not use the term heat setting for a cotton fabric. The term that is used for a cotton fabric is equalizing. Let's see what is done in heat setting. As we have discussed, heat setting is carried out to achieve shrinkage control and to improve the dimension stability of the fabric. The principle of heat setting is that we increase the fabric temperature to a point where the secondary bonds are broken. Secondary bonds could be dipole interactions, etc. For example. And at that temperature, we keep the fabric at a sufficient time for the polymer chains to settle in new positions. So the new positions that the polymer chains acquire are stress-free positions. And in this condition, we reduce the temperature again, and the polymer chains are locked in their relaxed state. So during the process of heat setting, the strain inside the fiber structure is removed. You must have discussed this in detail in your TS 245 course. One requirement for printing, which is perhaps obvious to a certain extent, is to ensure that the fabric is crease-free during printing. Because if creases are present in the fabric, then the area under the crease will not be printed. And after printing, it will appear as a white unprinted area. Now, why is this problem of creasing so important? Because depending on the machine condition, there are chances of excessive creasing in bleaching. There is also a possibility that such creases become rather permanent, and therefore we face all sorts of problems in subsequent processes. Crease formation in a fabric is also possible on a machine if the fabric tension varies. In order to address this problem, a certain type of roller arrangement is used on almost all open width continuous processing machines. These rollers that you see in the image here are called expander devices or expander rollers, and they are being rotated with the help of motors at very high speed. And because of the threading on their surface, they remove the creases from the fabric. Now, apart from these requirements, which are common for all textile printing operations, there can be some special requirements as well. For example, in inkjet printing, we are required to apply certain chemicals and auxiliaries onto the fabric before printing. We are going to have a look at this in greater detail in the lecture, which is specifically related to inkjet printing. But that lecture is right towards the end of the course. Now let's discuss some quality control checks that we need to perform before a fabric is taken to printing. We need to test the absorbency of the fabric. For this, we use different standard test methods. For example, the AATCC test method 79 or any relevant test method from ISO or other methods. The selection of the test method depends on the practice of the printers, or sometimes the customer who has placed the order for a printed fabric will also specify the test method. Similarly, there are standard test methods for shrinkage control. Here in the image, you can see the shrinkage template for the AATCC test method 135. The test method 150 from AATCC can also be used to measure shrinkage. And then, of course, there are ISO and other methods available as well. As we have discussed, we will also be interested in measuring the bow and skew in the fabric. So there is a standard test method for for measurement of bow and skew also. But here in the images you can see there is a simple formula that we can use to calculate the bowing percentage and the skewing percentage. So you measure this gap here, the gap where the bow is maximum, and divide it with the width of the fabric. A in this image is the width of the fabric, and this number, this percentage, is referred to as the bowing percentage. A similar formula is there for skew percentage as well. We are, of course, interested in in getting a certain degree of whiteness in the fabric before printing. This is more important in case of designs which are known as low coverage designs, such as the one shown in this image here. If you look at this design, you will see that a lot of ground fabric, the white unprinted fabric, is visible after printing. So if we are printing such a design, we will of course be very interested in the whiteness of the ground fabric.
Another very important preparatory requirement is to control the pH of the fabric before printing. Ideally, you would like to print on a fabric that has a neutral pH. If there is any alkali, for example, left over from the prior bleaching process, then it can result in all sorts of unwanted interactions with the printing inks and the printing process. For example, if there is any alkali present in the fabric, making its pH slightly alkaline, then the fixation of pigment print could be hindered by that. There are other unwanted effects as well, but the scope of this lecture is to not talk about the preparatory processes in great detail. And yet another important fabric parameter that we need to check is the electrical conductivity of the fabric. Fabric can be slightly electrically conductive due to the presence of an electrolyte, for example salt. Now the question is that where could salt come from on a fabric? Salt could also be produced during the preparatory processes such as bleaching. And if salt is present in the fabric, then again it can interact with the printing ink in unwanted ways. For example, if there is a considerable amount of salt, or in other words, if the fabric electrical conductivity is fairly high, then this can result in loss of the viscosity of the printing ink when it is applied on the fabric. And if we do not have complete control over the viscosity of printing ink, then it can result in unwanted excessive penetration or spreading of the ink. These sorts of phenomena can severely affect the print quality.
Let's summarize what we have discussed in this lecture today. Preparation of a fabric for printing starts with the usual pre-treatment operations, which are designed to clean the fabric and to achieve the desired degree of whiteness and absorbency. In addition, in case of printing, we are very seriously concerned about web distortions, and we try to ensure that web distortions are removed prior to printing. In addition, the fabric should be dimensionally stable and its shrinkage should be controlled as much as possible before printing. During printing itself, the fabric surface should be free from any surface depositions such as dust, lint, or loose threads. That's the end of this lecture. Thank you for your attention. See you in the next lecture.